This video and the ones that follow in the RC Semantic teaser series are intended to demonstrate some of the features that I've incorporated into my simulator, which is an ongoing project that I've now decided to complete in conjunction with now making OpenGL programming tutorials. The code snippet that I'm showing you is a close copy of the Vertex shader code that is used in the simulator. The Vertex shader performs most of the work, and therefore for this short demonstration I won't be showing the fragment shader code or the C++ code on the CPU side. It's worth noting that the GLSL shading language has various built-in functions, some of which are being used here, namely the transpose function, the inverse function, the absolute, the radians, cosine, sine, and the normalize function. Within the bend main blades function, it starts by identifying which of the two blades is being rendered, and then calculating how far along the blade's length the current vertex is located. The total amount of blade bending is calculated by multiplying the RPM factor, which is based on the RPM and the collective stick input, by an adjustable sensitivity setting, but bending can also be added manually by operating one of the control panel sliders with the mouse or by using the keyboard. The radius float variable starts off at a value of 100, which results in virtually zero bending, and is then reduced based on an exponential calculation. I've also included a setting which allows you to adjust the blade bending characteristic based on an adjustable multiply value, which when multiplied with the vertex Z position value results in a non-linear effect. The main aspect of the bending calculation is based on mapping, or wrapping, the straight length of the blade around 1/4 of a circle's circumference, and then using some basic trigonometry. First, the length of the blade up to the vertex Z position is divided by 1/4 of the circumference of a circle that has a radius equal to the previously calculated radius. The resulting value is then used to calculate the percentage angle of the 1/4 circle in degrees by using the radians function. And then cosine and sine are used to calculate the vertical and horizontal displacement for the current vertex. Also notice the two if statements that are being used for reversing the horizontal displacement direction. Next is to consider how the normal vectors need to be modified. Ordinarily, each normal vector is just multiplied by the model matrix for any given mesh, but here I'm also generating a rotation matrix based on the circle percentage angle calculated previously. The transpose of the inverse of the model matrix is then multiplied by this new rotation matrix to produce the resulting normal matrix, which is used in the lighting calculations. And then finally, the vertical and horizontal displacement values are added to the original vertex position values. In Blender, we can select one of the blades and then enable edit mode, which allows us to manipulate the individual vertices that the mesh consists of. Manipulating vertices in 3D modelling software is equivalent to manipulating them in a vertex shader, whether you're using OpenGL or any other graphics pipeline, such as Direct3D. By selecting Blender's proportional editing tool and using it to manipulate the vertex positions, it's possible to replicate in a similar manner what the simulator's vertex shader is doing during each invocation. Notice that the blade along its length is divided up into lots of small sections by the horizontal edges across the width of the blade, which allow the blade to bend and be distorted. At this stage, it's worth having a quick look at how UV maps and texture coordinates come into play. By selecting Blender's UV editor view, we can then change which texture image coordinates the vertex position values correspond to, the image of which is applied to the mesh faces.